Okay, so to this point, we know whole bunches of things about solutions. All right, we learned KSP in chemistry 2, and then we learned a little bit more about it. Here's what's next. KSP is called the solubility product, and it is the equilibrium constant that dictates how much ions go into solutions, the concentration of ions in solution. So for something like calcium sulfate, most sulfates have solubility issues. Only the group 1 sulfates and ammonium sulfate can be guaranteed soluble in water. That will set up an equilibrium that puts me some calcium 2+ and some sulfate and ion into solution. Okay. And there's a couple of things that we can do that mess with that equilibrium. Like, what if you added more sulfates? What would that do?
It would cause the reaction to shift back to solid.
Yeah. So if we added a common ion, if I were to add sodium sulfate, well, that's a strong electrolyte because it's a sodium salt, and all sodium salts are soluble. So we know that this would split apart completely in solution. And now this is what we would call a common ion. And the common ion effect is your KSP is products divided by reactants. Our reactants are solids, so they don't show up. But basically, the equilibrium position here says you have too many products. So go ahead, oh, I did the wrong one, and move your equilibrium back from whence you came and turn those too many solids back, products back into reactants. Okay? What does the sodium do?
You said it's a spectator ion.
Yeah,
Isn't it? No?
it was up until today. The sodium, we have been told, is not common to the calcium or to the sulfate. It is a spectator. It's a strong electrolyte. It just sits in solution and does nothing. It is happy being its ion, because its ion has 8 valence electrons. The atom that it came from only has 7. So it will just swim around in its ionic form. Okay? And ions in solution look like this. There's the sodium. And we're only really ever going to deal with aqueous solution in analytical chemistry. It will point it will have water point its negative end towards that positive ion. Conversely, the sulfate, which I'm not going to draw out, but having said I'm not going to draw it, I really have to do it. Bigger,
Yes.
right? And is in resonance, there's delocalization here, that any one of those 4 oxygens could have the negative charge. 2 of them we draw as pi bonds. 2 of them we draw as single bonds with the negative charge so that it meets the octet rule. Okay, so So I have a negative on the outside, so water is going to surround this way. It's going to put its positive end this way. And I haven't looked up recently what's going on in the world of solvation sphere chemistry. I do remember from my own studies that there is a primary solvation sphere. Our book calls this an ionic atmosphere. I don't like that at all. Don't like that.
Why not?
Because it says atmosphere. And they're in solution. Don't like it. This is called, what did I just call it? Solvation sphere. This is a solvation sphere. As is that one. Now that's your primary solvation sphere, because this is the first set of solvent that meets the ion. But look at the perimeter here, there are only hydrogens. And the hydrogens are on the losing end of all of those polar bonds. So the outside of this is positive, which means that the next set of waters will also point their oxygens towards these hydrogens. And you get a secondary sphere. Now at some point, nothing here is holding tight. Everything's interchangeable. You've got billions and trillions of water molecules, and they're shoving each other out of the way because they have kinetic energy. And they're all interchanging. But we have the same thing, that they basically are oriented inward. I'm going to say that phrase out loud. What was it? Ionic atmosphere. I'm not going to write it down. And we get the reverse here. Now there's a tiny bit of science going on here that is a bit counterintuitive. All right, what do we know? Let's pick two elements in the same period. Okay.
Which period?
Nice easy one. There's sodium. There's chlorine.
Yes.
Okay. Here's the sodium atom. Dot. There's a chlorine atom. Which one's biggest?
Sodium.
Yeah. That's not what people are expecting. The sodium has less protons, less neutrons, less electrons. The chlorine has more protons, neutrons, and electrons, but protons and electrons attract each other, and all the protons go to the same space. They all go to the nucleus, so the electrons all move in to see them. So we get a contraction as we go across the period, and the chlorine is smaller than the sodium. When I make these be ions, this now has no electrons, and that has 8. What happens to the sizes? They more than switch. This one gets tiny. gets bigger.
Why is that?
For the exact same reason as the others. It is called effective nuclear charge. That previously I had sodium. Sodium is in position 11 on the periodic table. It's got 11 protons in its nucleus. 2 electrons outside of it, 8 electrons outside of that, and then 1 on the real perimeter in the valency. If I lose that electron, I go down a shell, which is already smaller. And now my 11 protons are shared amongst 10 electrons. So the attraction between all 10 of those electrons, they now see 1 additional proton. So they get even closer in. So cations contract and anions expand. Okay. Now when you get to be really, really tiny, you gather more of a crowd. So the size of a naked sodium, the textbook will tell you, is this small. But when you surround it with its primary and its secondary sphere, it might be bigger in solution, effectively bigger, not really bigger, but effectively bigger than other ions that on the table of ionic radius are actually larger than it. Great big ions might gather, so all of that positive charge or all of this negative charge is now dispersed over this whole surface area. It's not as attractive. It's not as attractive to the solvents. Whereas you get all of that highly positive or highly negative. So fluorides and lithiums, little, they have what we call a high charge to size ratio. They're little tiny ions that in solution are effectively larger than the other ions that are lower down in the group from them.
Does Gould's law help explain where that's the
Yeah.
thing?
Okay. Now, so the sodium is an ion in solution, and the sulfate is an ion in solution, but the sulfate was a common ion. What happens if I had sodium chloride? Let me put my equilibrium back to where it was to start with. I have calcium sulfate. It is a partially soluble salt. Most of it stays in solution. Some of it becomes calcium ions and sulfate ions. Sodium chloride, most chlorides are soluble. All sodium salts are soluble. Strong electrolyte, 100% of this goes into solution, 100% of that goes into solution. General Chemistry 1 and General Chemistry 2 tell us there is no effect on the equilibrium. That's not true. What happens is this. Your calcium sulfate is now more soluble in salt water than it was in pure water. You want to hazard a guess about how much more? I'll leave space here. would be impressive.
10 times.
Oh, that would be. If it were 10 times larger, we wouldn't be able to hide it from the general chemistry students.
Okay, that is true.
It's up to 30%. So something's going on. Something is going on. And we've done this in lab. At some point in lab, we have taken a separatory funnel that has an organic layer and an aqueous layer. If it's a hydrocarbon, the hydrocarbon's in the top layer. If it's got a halogen in it, it might be in the bottom layer. Okay, let's say that this is the organic layer and this is the aqueous layer. And something polar has been made here. And I want to extract it into the aqueous layer. What we've done is we've added distilled water in here and shaken it and let this transit and be extracted out of one layer into the other. And at some point during the lab, because you just read the procedure and you go, okay, let's do that now, let's do that now, let's do that now. Instead of using just water, we used saturated sodium chloride solution. Does that even ring a bell? No, because it was a line in the procedure that you did, and then you moved on. If, instead of being pure water, this was salt water, this water is now more polar. It's more polar. Salt water is more polar than pure water, and the polar thing gets extracted into it easier. And sometimes we want the product to move this way, but more times than not we want to remove impurities. We've got a polar impurity and we want to remove it out. And it's called salting out. That you throw some salt water in there, you shake it, and you pull all the polar impurities out of your reaction, and your good non-polar stuff goes on to the next step. Okay. Salt water is more polar than pure water. We're going to call this ionic strength. Ionic strength of the solution. I'm going to tell you that the ionic strength describes the solution. Okay. When you read this back and it says strong electrolyte, you're going to know what that means, right? What's a strong electrolyte? It dissociates into its ions completely. So, our solubility rules from chemistry 1. All sodium salts are soluble. All nitrates are soluble. All potassium salts are soluble. So if your salt is a group 1 nitrate or an ammonium salt, then it's guaranteed to be soluble. Now, if it's a chloride, chlorides are not guaranteed to be soluble. Silver chloride's not, mercury chloride's not, cadmium chloride's not, lead chloride is not. But if I attach it to a sodium salt, then it has to be. Okay, so the fact that sodium chloride is a strong electrolyte has nothing to do with the chloride, has everything to do with the sodium. The ionic strength of a solution is increased by adding a strong electrolyte. It promotes dissociation. Dissociation into ions. Increases the solubility of these things up here, the calcium sulfates, the barium sulfates, the silver chlorides, the cadmium chlorides, cadmium and mercury chlorides, these insoluble salts that we talk about, we call those sparingly soluble. Increases the solubility of sparingly soluble salts. Okay. So we should probably try to define ionic strength quantitatively and then figure out, can we attach ionic strength to concentrations in solutions and see what the effect is? That would be really, really cool.
No.
Yeah, okay. So this ionic strength is going to generate something for us. Now, the full formula for how it works is something you will never, in this class, you will never need. Possibly in physical chemistry. It's part of the Debye-Huckel equation. And Debye-Huckel equations are about, you have an ion, it has a size, it has a charge. What is it doing to the rest of the world? Okay, and a positive and a negative will attract each other from a distance, and when they get close, the outside electrons will say, that's far enough, and then they'll repel. So you can use the Debye-Huckel equation to just basically say, this is where the atoms should be sitting. This is how far apart they should be. Okay. So we're going to define this thing, ionic strength. It's going to feed into an equation, and that equation is going to give us something called an activity coefficient. And the activity coefficient is going to be a number that we use to modify concentration. In the same way that PV equals nRT, the ideal gas equation, works over a range of values for pressure and for volume and for temperature and for numbers of moles, so therefore concentration. And when the gases are warm and the volumes are large and the pressures are low, PV equals nRT works over a linear region. But you make the gases be cold, or you make them be under pressure, and then they deviate from ideality. and we have to turn the ideal gas equation into either the virial equation or Avogadro's, the Van der Waals equation, where we say that our gas molecules actually have a finite volume, because we've always pretended that the gas is not occupying any volume, and that there is an attraction between them when they're close. Okay. When the gases are far apart, we're saying there's no attraction and there's no discernible volume. Okay. So under some circumstances, we just use pressure. Under other circumstances, we have to modify it. And beyond the virial equation and the Van der Waals equation, only the Van der Waals equation is in the general chemistry textbook. There's something called fugacity. Fugacity is an altered pressure. It's the ideal, it's the non-ideal pressure. It's the real pressure. It's the pressure that has been modified by a value that we can find. Concentration is going to go exactly the same way. Under some circumstances, concentration is fine. When you have just these ions in solution, you can just go with concentration. But when you have lots of ions in solution, this ion might be messing with this ion, in which case concentration has to go away and be modified. And when we modify it, it's going to become called activity. Okay. So ionic strength will lead to something called the activity coefficient. Activity coefficient will act on concentration and give us activity. Ionic strength. Let's think. Now it is possible just to have a guess. Maybe not. M is a metal. X is a non-metal. I've made a salt. This salt is only partially soluble, and it makes M plus and X minus in solution. Okay? Ionic strength is given symbol mu, and mu is equal to half of the value of the concentration of the ion multiplied by its charge. Z, we wrote Z effective on the board a minute ago, is charge. And that is going to be squared. Oh, yeah, two brackets. Plus the concentration of the X raised to its charge. So this is just concentration, and then that's a charge. This is concentration of the anion, and then this is the charge of the anion. And if you only have 2 things in solution, this is all you need. If you have 8 things in solution, you have to count them all. Okay? So our textbook definition is the ionic strength mu is half of the sum of, they like to call this I, but it could be, if I make it N will work, right? The sum of all of the N numbers of things that you have, concentration of N, charge of N squared. So however many you've got, if you've got 8 ions in solution, you do concentration the square of charge plus concentration square of charge. Okay? Let's do an example. or 2. Oh, and while we're here, while it's up, because this term is squared, what that means, right, because that term is squared like that, it means that if you have 3 pluses, they're more important than 2 pluses, which are more important than 1 pluses, and 3 minuses are more important than 2 minuses, and more important than 1 minuses. They have more of an effect. Okay? All right. Let's do an example.
Didn't we do some like this last year? Camp too?
Not this thing.
Looks familiar.
Okay. Not this particular thing. If I have a 0.1 mole per liter solution, this one is just straightforward, of sodium nitrate. All right, first of all, I got to figure out what my ions are. That when this breaks apart, it isn't a sodium and a nitrogen and 3 oxygens. It's a sodium and a nitrate. Okay, so I've got to think that in solution, that's an Na plus and an NO3 minus. All right, all nitrates are soluble, all sodium salts are soluble. This is a very strong electrolyte, guaranteed to be soluble in water. All right. So, mu is half of the concentration of the sodium multiplied by the charge of the sodium squared, plus the concentration of the nitrate multiplied by the charge on the nitrate squared. And I need 2 sets of brackets for that. Okay, so this is one of the 2 multiplied by the concentration of the sodium.
0.1.
Yeah, so if I have one of these, it makes one of those and one of those. So if I have 0.1 of these, it makes 0.1 of those and 0.1 of those. That's why you need a balanced equation. It really goes back to kind of high school chemistry of the first thing that you should do is write a balanced equation.
That'll apply for this one too?
Yeah.
Just balance it at first?
One of those makes one of those and one of those. And that means that if I put 0.1 moles in, it makes 0.1 moles here and 0.1 moles there, which means this number right here is 0.10, because that's how much you got in. Multiplied by the charge on the sodium. There's the charge on the sodium. It is 1, and I'm going to square it. 1 times itself is 1. 1 times 1 is 1. Plus my nitrates all had to come from the sodium nitrate. So I have the same thing going on that I had with the sodium. And now my charge is -1. And the square of -1 is 1. If you don't believe me, do it on your calculator. All right. 0.1 times 1 is 0.1 plus 0.1 times 1 is 0.1. Add those two together, and you get 0.2, and then divide them by half, and you get 0.1. That the ionic strength for this salt is just 0.1.
What's the unit? Is there a unit?
It's what?
Is there a unit or?
Well, technically, that's still in molarity. We haven't done anything to it, but we just leave it be. It's dimensionless. That's too simple, isn't it?
Yeah, that is.
Yeah, let's do a hard one. You got that? Yeah. All right. Let's do. Did they use the clock in here? I have no idea what time it is. I'm not wearing a watch.
11:42 or 40.
Okay. How about? I did bring a second example. Yeah. 0.01 moles per liter sodium sulfate. Okay? This will change things up. Because previously I had just a 1 plus and a 1 minus. Sounds like they're going to knock each other out. Think so. This one won't. Because sodium sulfate is a sodium salt, so it's guaranteed to be soluble in water. Puts 2 sodium ions, because the sulfate ion is an SO4 minus. Okay. Mu here is half the concentration of the sodium multiplied by the charge of the sodium squared plus the concentration of the sulfate multiplied by the charge on the sulfate squared. Okay. What's the concentration of the sodium?
0.00.
Ooh.
No, it's.
I did bring a different colored pen today. All right, this is why we need a balanced equation. 1 sodium sulfate is equal to 2 sodium ions and 1 sulfate ion. So if I had a mole of this, it makes 2 moles of that. If I had 0.1 mole of it, it would make 0.2 moles of that. I have 0.01 moles of this. Therefore, this is 2 times that amount. And then multiplied by the plus 1 squared. So 0.02 times 1 equals 0.02. Now, on the sulfate side, whatever sodium sulfate went in, 1 to 1. They are a 1-to-1 stoichiometric ratio, which means that the concentration of my sulfate is the concentration in the question. And I'm going to multiply that by the square of the charge on the sulfate. And the sulfate is -2 squared. -2 squared is 4. So this gets to be 0.04. 0.02 and 0.04 is 0.06. And then you take half of that, and this becomes 0.03. Okay. All right. Ionic strength is a way of looking at your solution and figuring out what its environment is. It is not the final answer. It is something that we are going to use on our way to finding a modified concentration. But
that was really like the first step.
yeah.
First step.
Now, here's where we're going to use it, and it isn't even in the equation I'm about to show you. The ionic strength isn't even in it.
What?
Yeah. The ionic strength is a column that you use in a table to find the real value.
Oh boy.
Okay. So concentrations in solutions that contain ionic contaminant, I'm going to call them contaminants, electrolytes. Those concentrations deviate from the ideal value. We're going to replace concentrations in complicated solutions. Simple solutions, you can keep your concentration. But
What do you mean? What's the definition of simple versus common?
simple's only got one thing in it.
Okay.
I've taken some hydrochloric acid and dissolved it in water. I am fairly confident that the concentration of that hydrochloric acid is what I think it is.
Oh, okay.
Activity is equal to concentration multiplied by this thing, which is called the activity coefficient. Okay? So we're going to go ahead and find the activity coefficient. The activity coefficient is the modifier that we can apply to the concentration, because chances are you know what the concentration is, or you know what you think the concentration is. But that's not the real number, because your solution isn't in pure water. It's in something highly ionic now. This is the modifier, which will change and give you this thing called activity that will take all of that into account. And it will tell you, oh yeah, your solubility is, your actual solubility is this other number, because you didn't take into account that you had sodium chloride in solution. It's something really ionic. Okay? All right, the activity coefficient, this guy, that measures your deviation from ideality. There's something very, very similar in the world of gases, that fugacity is pressure modified by the fugacity coefficient. And do we have anything else to say about it? Yeah, it depends on ionic strength. So we need to know the ionic strength before we can find the activity coefficient, which we will then use to modify the concentration and reveal a better number. All right, let's do a couple of these. Let's go back to calcium sulfate as a solid, making calcium ions in solution and sulfate ions in solution. All right. KSP for this, if it's in pure water, is just that concentration multiplied by that concentration. Let's do this again in the presence of strong electrolytes. Remind me again what an electrolyte is? Ion in solution. If it's a strong electrolyte, that means it has split apart completely. All right, so the KSP is now this number, the activity for the calcium 2 plus multiplied by the activity of the sulfate. All right. Well, not a problem, because I can just use my concentrations and this modifier. So that is just what I already knew is the calcium 2 plus, and then the gamma, specifically for calcium 2 plus, multiplied by concentration of the sulfate, and the gamma of the sulfate. Okay. If we left it here, that would be too easy, because this is 1 to 1 to 1, and we know that equilibrium, if you have coefficients in your equilibrium equation, then your equilibrium expression uses those coefficients as powers. Yeah? So let's do that again. So that's just an example of how to write it out. Let's do it again. What if I had aluminum? Aluminum is in group 3, has a 3 plus counter ion. What if I made aluminum sulfate?
You have AP?
That's an Al. That's my L's. L. Three plus 2 minus.
So 3, 2
I'm going to need to make this be 6 pluses and make this be 6 minuses. That's a 3 plus and a 2 minus. You just move the numbers. Your 2 minus, your 2 goes here, and your 3 goes there. and sulfate. How many aluminums?
2,
How many sulfates?
3.
Okay. So KSP for this is the activity of the aluminum 3+. Raised to the power of its coefficients in the balanced equation, squared, multiplied by the activity of the sulfate, raised to the power of its coefficients in the balanced equation. Okay? Now we don't know what the activities are, because we haven't found the ionic strength yet to know what this modifier is. So I'm going to take that and rewrite it in these terms. That the KSP is the concentration of the aluminum raised to the power of the number of times it appears in the balanced equation, multiplied by its activity coefficients, the one specifically for aluminum. I'll show you probably Tuesday now, because we're running out of time, how to find those. That gets squared too, because this is an item. Multiplied by concentration of the sulfate. So 4,2 minus. And there are 3 of them in the balanced equation. So this gets cubed. Multiplied by its gamma, specifically for the sulfate, also cubed.
If I were to like write that in parentheses, like the activity, like the concentration gamma, parentheses squared, is that okay?
I think so, yeah.
Okay. That way I
Oh,
just
wait,
further-
what have I done here? I've raised that to the wrong number, haven't I? No, I didn't.
But like, for example, like whatever
Yeah,
that item.
2, 3, 2, 2, 3, 3.
Yes.
I think so.
Okay. Like, I don't think so.
I think so.
Okay.
Yeah.
Cause that way I don't forget to square something. That's
Mhm.
my thing, I'm gonna forget.
Okay. What's the time?
11:58.
Okay. Let me show you the table. We have a table. This is table 8.1 in the textbook. It is on page 166. And it lists ions by the charge. So it doesn't matter if you are a 1+ ion or a 1- ion, because that's Z, we're squaring that value, so it doesn't matter. All the 1 minuses and 1 pluses are here, then the 2 minuses and the 2 pluses are here, and the 3 minuses and the 3 pluses are down here. There's a problem with these numbers. We've kind of seen it already. When something is very highly charged, 3 and above, but we start to see it at 2, but once you get to 3+, 3-, it's real. They don't dissociate completely. And so even this, which is the value that's going to fix the concentration, this will still be wrong. So We're good for the 1s and the 2s, not so much for the 3s. Okay? It has values in all of these columns, and those columns correspond to what the ionic strength is. So when your ionic strength is this value, you go find your ion in that column, and it tells you what its activity coefficient is. So they can all be looked up. There's no calculating that. These are found in a table. Okay. So once we know that we need them, and we know how to use them, the value is found in a table. Our particular one for our book is in table 8.1, and it is for a specific value of ionic strength. And what symbol did we give to ionic strength?
Mu.
Mu. And what is this called?
Gamma.
That's a gamma. Okay. When we come back, we'll put the numbers from the question in here. We'll find the numbers from the table, and out will pop a modified value. Okay? Do that on Tuesday.
Okay.
Something to look forward to.